Hello everybody and welcome back to another video by Funland Tutorials. In today's video, we are going to be discussing about how we can apply the iterative process for AR1 series. Now in my previous video, I had discussed a very brief and a very intuitive explanation of what actually is an AR or an auto-regressive DGP and what we mean by the order or order P of that particular auto-regressive function. So generalized notation is ARP, and in today's video we are going to be learning how we can apply the iterative process for an ARP equal to 1, so an AR1 series. I suggest you have a very brief overall idea about the the concept of the AR function by looking at the video that I have posted last week. The video will be uploaded already, and it will have been linked somewhere up in the top right corner of this video somewhere, and even in the description box below, so do give it a view. Now if we want to apply the iterative process, what this iterative term means is you keep repeating it. It's a very common term, and what we do is we keep applying the same method in loops, and that is called an iteration. That is called looping of a particular function or an action or something of that sort. Now let us recall what the AR1 series looks like, right? So you have an auto regression, so this yt will of course depend on past values of yt, no doubt, but there is a constant involved. So you have phi naught, that's the constant that is involved, independent of time. So it does not depend on time. Whatever the time period you consider, there is going to be this constant component involved. Plus there's going to be a fraction or a multiple, phi 1, that's a constant, which is multiplied to the past value of yt minus 1. That can be, if t is measured per day, then its past value, it's yesterday value. If t is measured per month, then this is the value for last month. If t is measured annually, then this is last year's value. So something along that lines. It's just one period back, one period lagged. So there's also a error term involved. There's an error term involved, epsilon t. This epsilon t essentially tells you, look, I know the value of the constant. I know the value of this constant term. I know the value of this multiple, phi 1 involved. I know the past value, but even if I have all these information, these are known values. These two are time independent, and this is the past value. So I can just ask somebody, hey, do you know what was the price of onions yesterday? They can tell me that, and these two, I have values that can help me determine these two values. But even if I have these information, there is no guarantee that I can actually predict yt. Right? If I can just ask somebody on the road and ask them for the price of onions, and suppose even I have the information, I can't just say, okay, then that means this will be the price of onions for today. I can't do that, right? There are some unknown factors involved. Those unknown factors are incorporated in epsilon t. There could be, just within a day, there could be some hoarding of onions, and that could have artificially raised the price of yt. That is the price of onions, which is yt here. So epsilon t is actually a current value. It's an unknown value, and you cannot, that it entails us to justify that we cannot always predict the value of yt. So this is the intuitive explanation. This is the intuitive explanation that we get from this type of expression for AR1. There is a different expression, and that we can generate from iterative process. Now what do we do in iterative process? Let us first put t equal to 1 in the previous expression. So if this is equation 1, let us put t equal to 1 in this equation. What does that give me? If I have t equal to 1, then this t becomes 1. So we have y1 equal to phi naught, because there's no t involved. I keep saying that this is a time independent variable, so even in period 1 there will be a phi naught component. Then you have phi 1, again it's a time independent, you don't see any t here, so phi 1. So let me just correct that. Yt minus 1, so it's actually y1 minus 1, that is y 1 minus 1, because I put t equal to 1 here, right? So why 1 minus 1? Now 1 minus 1 is 0, so we can simply put y is 0 here, plus epsilon t. So epsilon t is epsilon 1, because again we are putting t equal to 1 here. So you get phi y1 equal to phi naught plus phi 1 y naught plus y epsilon 1. So y naught is the value in the 0th period. It's 0 period, we call it starting point. So y naught, that determines y1, and there is also a current value epsilon 1 error term involved. Again, we put t equal to 2. Herein lies the iteration. We are doing that same thing, but this time we are going to put t equal to 2. There's just a slight manipulation of the action, otherwise it's the same action being repeated again. So you have y2. What do? You put t equal to 2, so you put y2. Then again, this is a time independent constant, so you put phi naught plus again a time independent constant phi 1. Then you put t equal to 2, right? So t equal to 2 minus 1 plus epsilon. Again you put t equal to 2, so instead of t you put 2. So you have, now you, instead of writing 2 minus 1, you can just simply write 1, because last time I checked 2 minus 1 was 1. So you have this expression, right? y2 equal to phi naught plus phi 1 y1 plus epsilon 2 being the error term for the second period. So now we are looking formally, we are focusing on the second period value. So for now, y1 is also a past value, y0 is also a past value. Now what we can do is, you see this y1 is the same as this y1, right? It has to be the same. So what we can do is, instead of y1, we can put this entire expression. So what we can do is, we put phi naught plus phi 1, and then instead of this y1, we can put this expression, because they are both the same. So we put phi naught plus phi 1 y naught plus epsilon 1. That gives you this y1, and then finally you have this epsilon 2, and you put it there, right? So you have this expression. Let us simplify this. So we have phi naught plus phi naught phi 1, phi naught, or actually we can take phi naught common as well, or maybe let me not skip steps. Let me not skip steps. So we have phi 1 into phi 1, so we have phi 1 square y naught, and then we have phi 1 into epsilon 1, so we have phi 1 epsilon 1 plus epsilon 2, right? Now what we are going to do is, we are going to do that same thing. So t equal to 3 this time, right? It's a very sort of a boring procedure, right? But that's what iterative process is all about. You see, I'm actually doing the same thing, but there's just a slight manipulation here and there, and that will essentially give you a drastically different outlook. I'm not going to say opposite, it's just a different outlook for the same thing. Same things can tell us different stories, right? It's just, we are trying to find out a different story, a different perspective of the same thing. So y3 this time, again the time independent part, phi naught plus phi 1 y2, and then we have epsilon 3, right? So current, the third period of the third value of y depends on the second value. That's just one period lag, as we did before. Again, this y2, if I can change the color, this y2 depends, is the same thing as this y2, right? Which is also again the same thing as this y2. So we can put this entire expression, right, instead of y2. So we can do that, and let me just use some bit of editing, and what we can find is, I'm going to give the entire expression here by magic, and there you have it. So not this thing. So you have phi naught plus phi 2, and I put the entire expression for phi naught plus phi naught phi 1 plus phi 1 square y naught plus phi 1 epsilon 1 plus epsilon 2, and you can't forget this little epsilon 3 here, so we have to put an epsilon 3 here. Now let us simplify this, right? I want to simplify it. So what I can do is I can multiply this entire thing, and you see, if I multiply this, we have phi naught y phi 2 and we have phi naught phi 1 phi 2, right? So what actually what since this phi 1 component is time independent, what we can do is this is going to be phi 1, right? Phi 1 doesn't change, it's time independent, so it depends, it's a constant, it remains the same throughout. So you see, if I multiply this, it's phi naught into phi 1, and then it's phi naught into phi 1 square, right? So you have a phi naught component everywhere. What we can do is we can take that phi naught common, and we can write 1 plus phi naught plus not phi naught, it's phi 1, because I've taken phi naught common. So this phi naught is here, this phi naught is here, and we have phi 1 remaining. We take this phi naught common, so we have phi 1 square here. That's one part of the term. Then you have, if you take an addition, then you have taken already these three terms. You have this phi 1 square y naught, and then you have a third part, that's phi, actually it's going to be 3 because there's a phi 1 multiplied to that. Then you have phi 1 square epsilon 1 plus phi 1 epsilon 2, and then there is the lone wolf epsilon 3 over here, right? This is the equation that we get when we put t equal to 3. Now we can keep doing that, right? If we keep repeating the same action and we put t equal to 4, t equal to 5, it's going to keep expanding because we have to keep putting in the previous values. So next time when we put t equal to 4, we have y4 equal to phi naught plus phi 1 y3 plus epsilon 4. Then we again put this entire big expression for y3, and it keeps repeating, right? That is the main idea of iteration. Now what we can do is, now we can go for something like an induction, or we can go for an intuition of types.